audio toolkit, that's not my main job. I work in a bank during the day, so I took a day off today. And I've worked in oil and gas before. I did machine learning, a bunch of things. But what I really do like is coding audio stuff in C++. I really liked the presentation about Stud Audio and Sol. So we'll see what will come up with all these new frameworks. But yes, my library is just a collection of classes. It's BSD. Works on Windows, Linux, Mac. It works with Juice, and it's also based around the same concepts as Traction at the time. It's modularity, reliability, and handles all the memory stuff. I've already presented that last year, so I won't delve on it a lot. So as Yvan said, there are lots of different classes, and I just wanted to add a new one. So the new one is about analog modeling. So last year, I did a presentation here. There were far less people, so I'm a little bit scared by all of you today. But one of the last slides was that huge slide, because it was also about analog modeling. It was just SD1, the Bose pedal, the SD1, and how to get from something that was really, really slow to something that was really fast. And then on KVR, there were discussions, and someone said, yes, I made a small library that was a Maestro that does parsing of spice and just do all that analog modeling on the fly. And I was just, yes, that's really nice, and that's really neat, because I don't want to start here and go all the way, all the time up to here. It would be really nice to have something that gets me, well, perhaps at least in between here before I can optimize everything a little bit more. And also that would work on a complex schema. It's not that complicated. It's just a simplified version of the Moog filter. So it's not that complicated. It's something that everyone wants to do, but still lots of equations, lots of transistors. So yeah, it takes time to write the equations and everything like that. And I don't want to write the equations anymore. I'm a little bit fed up by, by doing that. When I did the SD1, it was really simple. Then I started actually doing a preamplifier with a valve in it, and I just kept on failing and messing up the signs. And Yvan is saying, yes, yes. And he knows that because he worked on, I used some of your equations for that as well at the time. And yeah, I don't want to do that again. It's really painful. And if you already have a netlist, it would be nice to have at least some code, or just to see if everything works. And that's what Spice does. We have lots of different implementations, and they give you some stuff. So I wanted to try to do that. But of course, it's not that easy. I want to do that properly. Last year, we had also a talk about unit testing and all that stuff. If I really wanted to do something properly, I really would like to do it tested and on simple schemas and also on complex schemas. So I started doing a pure Python implementation first, something that would just help me trying to figure out all the different bits and pieces. Then progressively, I would, and I will show what I did, try to add the C++ side, but just generate all the components on the fly, and then try to have a JIT version. And of course, Jules has also talked about JIT, and I was just doing that presentation. Oh, he's also talking about that. Oh, too bad. But yeah, so I also have a JIT somewhere, but yeah, let's start with. So analog modeling, basically what lots of people do is start with is Nodal analysis. Basically, it's the Kirchhoff current law. You say that all the currents that go up to a point in your in your schema, all these currents should sum to 0. And then from that current, if you have a resistor, or capacitor, or something like that, you can infer the voltages on the different sides of your connection. So that's basically nodal analysis, as far as I understand. But it's not perfect, because if we go back to the Moog filter, for instance, as I said, it's a simplified version. But here you have an op-amp here, so that's a perfect component. That doesn't exist, but it's still nice to have such simplified stuff, simplified components. And that one doesn't work well with nodal analysis because it has its own equation. It's not the current law. It's, yeah, I'm multiplying the current and, yeah. So it doesn't work for nodal analysis, or it doesn't work for all circuits. So you have to add new equations that gives you modified nodal analysis, as far as I understood. Last year I messed up and I said something, so please tell me if I'm doing wrong, if I'm still wrong in my definitions. But yeah, that's the idea. So you have, after that, a set of equations, okay, with the current and perhaps for some additional components that have a specific behavior. So then, in my presentation last year, if we go back here, I'm going to go here for other people. One of the big gains that I got from when I moved from these different states here, different trials, was to use what's called state space components. Once again, as far as I understand, that's the definition. So basically, instead of using capacitors or coils and the original derivation, which is for capacitors, the current equals C times the derivative of the voltages, you use a mix of a resistor and a state, which is the current generator, and you update the state of the current each time, at each iteration. So I'm going back to, so I didn't put anything else here, but it's basically that idea. You replace all the complex components that have a derivative or something like that by something that is really simple, so that your equations, when you go back here, you don't have any time here, you just have in, you don't have in of t minus 1, you just have in of t. And that simplifies the equations, and trying to, especially when you write them, otherwise it's just horrible. Of course, once you have these equations, that's what you want to have, fx equals 0, x being the state, the different currents, for instance, the different, well, not the current, the voltages that you have in your circuit. And I'm using just Newton or Raphson to get to that actual state where you have all the sums of the currents equals to 0. And from that, you can then get your voltages. But that's all the mechanics that we have. But, as I've said, we start from the schema. That's where SPICE comes in. So that's the official way of describing a circuit. If you are here, probably you know that already. And there are lots of implementations, as I said, lots of free one, light SPICE, but all the electronics packages usually have also a SPICE modeler. And it's really neat because you can just have your netlist, and you have all the current all the currents in your circuits, all the voltages, etc. So that's, as I said, that's the goal of the ultimate goal is to have something that can run like SPICE, but in a plugin. Of course, although that's what we would like. So that's just a small description of the beginning of the Moog filter. So that's the SPICE netlist. You start with or that's some of the voltages that you have, and you say that, for instance, for that current here, you have a connection from the ground to S3B, which was the base of one of the transistors, and you have a fixed voltage which is 5, well, for instance. And then you have more components here. That's the description of some transistors and some of the capacitors, and you need to parse that. And I have to say it's hell to do that in C++. So I tried with Lex, I think, and Yak. It's horrible. So then I tried that with Boost Spirit, and it's even worse. And then Boost Spirit X3, which is the one that we are supposed to use, and there are no tutorials, no documentation almost. But it works for simple cases, and as I have to say, that's what I'm interested in. I even simplify sometimes the schema. So for instance, if I go back to the original Moog, so you have here voltages that are actually on top of others. And I said, yeah, but that's easy. That I can modify the netlist and just say that that's 6 volt up to the ground, and it's simplified. Because otherwise, it's so complicated to handle all these cases with Spice. And I don't want to write also a parser for all the equations that you can have also sometimes in Spice. In the netlist, you can specify your own equations. I'm not doing that because writing a symbolic expression, that's something for Jules, that's not for me. And now I lost my mouse somewhere, so let's go back to where we are. Okay. But at least with a Spice, with a parser, I can have kind of an AST and the description of all the different components. I have also all the different models. So for instance, all the transistors have a specific description. I know what's VT, I know what's N, all the different factors that are in the transistor, and that's all factored here. So I have a list of the components and the list of the models. So with that, I can actually automate the writing the model, the full model. So that's the first step that I did. Well, no, the second state. Once I had the Python working, I did the same with in C++. So basically, you have one component. All these resistor capacitors, all that stuff is all components. You have different implementations on the bottom, because that's the way we do that in C++. And they all have stuff that are redundant, right? I mean, resistance, the resistors, sorry, it's for the French. We have the same word for the resistance and resistor, so it should be resistor. For a resistor, you just have a simple way of computing the current. You don't need to do anything. It's just resistance, or the resistance, and you have the current. For a capacitor, as I said, you have the state space implementation, so you have to update this. So all these components have all the same APIs, and we all say, okay, you can pre-compute something if you want. But that's only useful for the diodes and the transistors. You don't need that for a coil, capacitor, or resistance. But for a dynamic filter, when you can have anything thrown at you, you need to, well, to say for all the components, do update yourself for all the different options. And then you have underneath them the actual implementation that is really simplified and doesn't have all that complex API. And that actually works. And as you can see, well, you see, I mean, I didn't show you the original one, but it's almost a match to the Lightspice version of the same circuit. There are some differences, but of course, that's because also Lightspice uses, I think it's a Pummel model for the transistors, when I use just a simple Haber-Maltz one, because you want to be as simple as possible, and I actually didn't even knew where to go to look for the equations. But basically, you have the input here, that's the big sinus, and the yellow one here is the output. And it's actually quite fast. If I do just a small profile then to see what is going on, in the Newton Raphson, you have a matrix inverse, and as it's supposed to be generic, I just use eigen, the pivot, the Householder pivot to get the result. And of course, you have lots of eigen, more or less all over the place, because that's what I expected. There are 11 voltages that it needs to compute, and so that's an inversion of an 11 by 11 matrix, and it does take time, so that's perfectly fine. But then you have all these places here where you have the pre-computation of the transistors for the exponentials. You have all the currents, all the steady state computation as well. That takes actually quite a lot of time. And that's just Valgrind. And Valgrind does give you some information, but it's not always perfect. But still, if all that space here actually is not relevant for us. If you already have the SPICE netlist, if you had a JIT, all that could actually go away, because you know what are the components, and you just use LLVM, and you have an optimized filter. And that's what I did then after. So that's the static filter generation, reusing all the different subcomponents that I had here. So instead of creating an API based on these components here, I just reused these elements here. Unfortunately, writing LLVM IR, once again, I'm not Jules. So I took the path of least resistance, which was writing a new C++ file, compiling it with Clang, then using JIT to the LLVM JIT to load it on the fly, and then get a result. So it's a bit more convoluted, I guess, than what Jules did. But still, it works. You have a result. You even have your C++ file, or the file that you can then modify, profile, etc. So that's actually a profile on not the JIT version, because I couldn't get the symbols back inside the JIT to get me all these information. So that actually, I took the same file generated by my JIT, well, not my JIT, but by my static filter generator, and I recompile it and then profiled. You can see I don't have anything with except for the eigen stuff. So all the rest, all the virtual calls can be removed, and even that one, I didn't actually optimize it, because it's still an 11 by 11 dense matrix, and that we know that it's sparse. It's really heavily sparse. So the future work for that would be actually to generate the inverse on the fly properly. Just my last slide, just to show you. So then did the actual just running time on 1 second at 86 kilohertz, and you can see that just a full compilation of a static filter that is really adapted to the schema is actually 3 times as fast as doing a dynamic one. And that one is actually, that's the JIT one. So that one is actually slower. I haven't measured it, but the exponentials is a little bit different in that one than on the offline because of some JIT issues that I had. But yeah, so there are lots of things that you can do once you have also a dynamic filter generator and the static one. The dynamic one is quite actually interesting because you could check what the behavior of the Jacobian is. What if you drop some of the elements in that Jacobian? Then once you have that, once you have profiled, checked the measures, then you can also tell the static generator, oh, actually drop some elements there as well and optimize your inverse. So that's a future work that I still need to do. But thanks for the attention. And if you have any question? It's dead silent.
Question?
I killed them. They're all dead.
Yeah.
Oh yes, I forgot to say that. Yes, that's actually relevant. Yes, sorry. So the dynamic part is a standalone module for my audio library. So it's available on GitHub as well. I should actually put that in the slides. So the slides will be on on ADC website as last year. I will modify them to add the link. The static one is still not finished, and I'm still not sure exactly what I'm going to do with it, if it's going to be a private project or not, but just ask me and we can figure something out, if you want.
Any other question? Okay, thank you very much for your talk.